This lecture covers section 6.3, planetary surfaces evolve through tectonism. Four processes have shaped the terrestrial worlds: impact cratering, tectonism, volcanism, and erosion. Tectonism is also called plate tectonics, which is known by the less precise name continental drift. The learning goals of this video are to understand what tectonism is, to be able to describe how Earth's surface has changed due to plate tectonics, to understand the role of convection as a driving force, and to describe tectonic disruptions on terrestrial planets. Tectonism is the deformation and movement of Earth's crust. The lithosphere, the Earth's crust, varies in thickness from about 7 kilometers to 35 kilometers. It consists of continents, primarily granite and oceanic crust, and slightly denser basalt. The lithosphere is brittle and rigid, but the asthenosphere, the upper part of the mantle, flows like a fluid. The crust is broken into plates. The map shows the distribution of Earth's tectonic plates. There are 7 large plates and a number of smaller plates. Continental drift and plate tectonics describe the movement of those plates. In 1912, Alfred Wegener, a meteorologist, proposed the continental drift theory. Initially, his proposal was scoffed at since he did not have training in geology. He was later found to be correct. These plates can separate, called a divergent boundary, or collide, called a convergent boundary. A third type of plate boundary is the transform plate boundaries, where 2 plates slide past each other. Most divergent plate boundaries are associated with oceanic ridges, which are underwater mountain chains that can stretch tens of thousands of miles. The Mid-Atlantic Ridge marks a divergent plate boundary between the North American plate and the Eurasian plate, where they are separating. The Atlantic Ocean is slowly becoming wider. Most of the world's volcanoes lie along plate boundaries. Each triangle marks a volcano, and notice how almost all of them line up with plate boundaries. Most of the earthquakes are also located along plate boundaries. The map shows the location of earthquakes. While earthquakes can be felt anywhere on Earth, all of the large earthquakes occur along plate boundaries. Subduction zones mark convergent plate boundaries. Here, 2 plates are being pushed together. As they do, one plate is forced under another plate, forming long, deep ocean trenches. The deepest parts of the oceans are along subduction zones. When 2 oceanic plates collide, the younger of the 2 plates, because it is less dense, will ride over the edge of the older plate. The older, heavier plate bends and plunges steeply through the asthenosphere, and descending into the earth, it forms a trench that can be as much as 70 miles wide, more than 1,000 miles long, and several miles deep. The Marianas Trench, where the enormous Pacific plate is descending under the leading edge of the Eurasian plate, is the deepest seafloor in the world. It curves northward from near the island of Guam, and its bottom lies close to 36,000 feet below the surface of the Pacific Ocean. Tomography is the study of the internal properties of a body by observing the behavior of rays passing through the body. Seismic tomography uses mathematical modeling of P and S waves that travel times the map velocity perturbations in the interior of the Earth. Similar to the process of a CT scan, the 3D visualization of the Tonga subduction zone in the South Pacific shows the subducting oceanic crust in blue. The Himalayas are formed during the collision of 2 plates, both made of continental materials. Neither plate subducts during continent-continent collisions, but folding and deformation of rocks does occur. This leads to mountain building. The Andreas Fault in California and the Alpine Fault in New Zealand are examples of transform plate boundaries. The movement creates slippage where linear features crossing the boundary get displaced. The driving force for crustal plates motion is convection. Convection is the rising and falling of hot and cold materials such as boiling water. Convection takes place in fluids and gases but cannot occur in solids. Convection pulls and thins the crust, eventually forming a rift where the molten magma seeps through. The youngest rocks are found at mid-oceanic ridges. Volcanoes occur at the mid-oceanic ridges where new crust is being formed and at subduction zones. As the oceanic crust is forced under the continental crust, it is heated and begins to melt. Being less dense, the molten rocks begin to rise through the cracks and eventually make it to the surface, producing a volcano. Between 1978 and 1988, laser ranging measurements were made between 22 ground stations across the globe using the Laser Geodynamic Satellite, LAGEOS. We know its orbit and the speed of light, so distances can be determined. Using LAGEOS, plate motion has been measured. Positive values indicate spreading and negative values indicate motion away. The motion is positive across rift boundaries and negative across convergent boundaries. Australia is moving northwards. The Pacific plate is shrinking and the Atlantic basin is growing. Using information of plate boundaries, we can project backwards the shape of the Earth's crust and the location of the continents. Mapping geological and climatological and fossil features across continents yields that the continents must have been connected about 500 million years ago in a supercontinent called Gondwana. The rocks in South America, Southern Africa, India, and Australia all reveal that they were once all under a giant ice sheet, the kind of ice sheet that can only exist at the poles. These 5 land masses were once connected and were all located close to Earth's south pole. The Earth, as it appeared in the Carboniferous period about 306 million years ago, during the Carboniferous period, the large coal seams were laid down. The Earth during the Permian period, 255 million years ago. The Earth during the Jurassic period, 195 million years ago. The Earth during the Eocene, 50 million years ago. The modern world. The world 50 million years in the future. The world 150 million years in the future. And the world 250 million years in the future. There are some plate tectonics videos that are recommended that you watch. Tectonism is only observed on Earth. However, all terrestrial planets and some moons also show evidence of tectonic disruptions. For example, figure 6.16 shows Valles Marineris, the major tectonic feature on Mars. This canyon system is more than 4,000 kilometers long. The image is from the European Space Agency's Mars Express satellite. Mercury's surface shrank after it cooled, leaving cliffs called scarps. These giant scarps are believed to have formed when Mercury's interior cooled and the entire planet shrank slightly as a result. Think of the shrinking of a grape into a raisin. Venus shows volcanic activity, but no sign of plate tectonics. Most of the Venusian surface is relatively flat. It is divided into 3 topographic units: lowlands, highlands, and plains. Tectonic features are present to a limited extent, and they include linear deformation belts composed of folds and faults. Earth is unique in our solar system in having its lithosphere broken into plates. No other planet has plate tectonics. However, all of the terrestrial planets have indeed seen some kind of deformation of their crusts, implying some kind of geological activity under the surface at some point during formation. Mercury's crust, for example, had an odd experience when it acted like a grape in the heat of the sun and shrank and wrinkled like a raisin. This left great cliffs in the surface, sometimes referred to as scarps. Mars has a mix of old cratered areas and younger, smoother areas. Mars's very extensive tectonism has resulted in many features, including the chasm Valles Marineris, the largest chasm in the solar system. Venus may be experiencing a different kind of active tectonism. Its surface is not broken into plates, but there may be spots of the crust that collapse on themselves, mixing with hotter material under the surface.